Hello class, welcome to today's lesson in which we're gonna keep looking at transformation of graphs, and today we're gonna look at the reflection. But first let's review a little bit very quickly what we did in the last class. Okay, I want you to observe this function f of x. What function is this? We don't care, it's just some function. Whether we know what equation is a representation of this function, we don't care for the moment. It's just an abstract function, okay? It's y equals f of x. So this is my function f. And look at the graph of it. Looks like an S more or less. And it crosses the y-axis at 2. Okay, so the first thing we can do with this is vertical translation, okay? And by doing in order to do that, what we can do is create another function which we can call g of x or whatever, any other name. And if g of x is the same as f of x plus a constant, what this is gonna produce is a vertical translation. If c is positive, this is going to produce a vertical translation upwards, and if c is negative, that's going to produce a vertical translation downwards. Okay, so for example, look at this one. Okay, look at this. That would happen. This would be the graph of this function. G of x equals f of x plus 2. Why? Because if you notice, this graph is the same as this, okay, with the only difference that it's displaced upwards by 2 units. Can you see? This one crosses at 2, this one crosses at 4. So there's a displacement of 2 units upwards, and that's why we can make sure that this function is g of x equals f of x, the same as this, plus 2. This is the new thing. This is the thing that produces the displacement upwards by 2 units. On the other hand, this one would be the graph of the function g of x equals f of x plus or minus what? Can you tell? Minus 3, right? Or you can also write f of x plus minus 3. It's the same, right? Why? Because remember, this one crosses at 2, and this red one is the same as this, but displays 3 units downwards. Okay, so we go from here to there, to minus 1. So that's how vertical translation works. It's an addition to the function, an addition or a subtraction of a constant c. Now we can also do horizontal translations. Okay, so remember, this is my original function, so to speak. And if I produce, for example, let's go first with this one, with the gray one. If I produce a function h of x, which is going to be equal to f of x minus 3, that's going to produce a displacement in the horizontal axis to the right. Remember, when we subtract or when we add a negative number to the variable, that's gonna cause a translation to the right. Okay, can you see? This point here is translated 3 units to the right by the inclusion of the negative 3 in the variable. And on the other hand, this function would be this graph would be the graph of the function h of x equals f of x plus or minus what number? What do you think? It's gonna be plus 4, right? Because, well, it's gonna be 4, that's for sure, because there's a displacement of 4 units with respect to my original function f. And it's gonna be plus 4 because the displacement is to the left. Remember, displacements to the left or translations to the left are done by adding a positive constant, okay, and as many units as you want the displacement. and displacements or translations to the right are done by subtracting a positive constant, as many units as you need. So don't confuse that. To the left, positive constant; to the right, negative constant. And this could be a source of confusion, so just memorize that. Okay, so this is translations, guys. Vertically, horizontally, also known as shiftings. And now let's look at reflections, which I think are a little simpler. Let's get rid of this. Let's go over here. Okay, so we have this function already prepared. F of x equals e of x, my exponential function, my good old exponential function. And let's see what happens when we attempt a new experiment. Instead of doing something like this, like I could do this, e to the x plus 2, okay, that's going to be a displacement, a vertical translation, right? Vertical translation upwards, or translation downwards, you see? Now we're going to do the following now. We're going to produce a function g, which is going to be the same or equal to minus f of x. And look, take a look at what's happening. Okay, this is my original function. This is e of x. And when I produce another function, when I create another function g, such that g is equal to the negative of f of x, what I can observe is that the original function gets reflected about the x-axis. You see, there is a reflection. And we achieved that by multiplying the function, the original function, by minus. I could have also written this, right? Like, and it's going to be the same. G of x equals minus e to the x, which is the same, right? If I deactivate this one, it's going to be the same. It's in black. Oops, there it is. Desmos has Desmos already knows what f of x is, which is e of x, because you already declared that. So this or this are exactly the same thing. So, okay, we can see what happens when we multiply the original function by minus. We're going to get a reflection about the x-axis. Okay, now what happens if I create another function? Let's call it h of x. And now I'm going to multiply just the variable, just right there, right there. Instead of x, I'm going to multiply it by minus x. So let's see what happens. Well, first I'm going to write it in the abstract form. Like h of x is going to be the same as f of minus x. And take a look at what's happening. One more time, this is my original function, e of x. And when I produce another function, h of x equals f of minus x, so the multiplication by minus occurs only within the variable itself, what we get is this new graph. And if you notice, this new graph is basically the same as this one, but reflected now around the y-axis. Okay? And I can do also the same thing I did before. I can write actually the whole expression. If h of x is equal to f of minus x, then that means that h of x is equal to e to the minus x. You see, it's the same. This and this are exactly the same expressions, and we get the same graph, of course. Okay, so basically, what's happening here? What is the takeaway? The takeaway is this. If you know the graph of a function f, and let's suppose it looks, I don't know, like so. It's kind of like a parabola or something, whatever, it doesn't matter. Then if you create a function g of x, which is going to be equal to the negative or minus this original function, then the graph of g will look similar to the graph of f, with the difference that is going to be reflected around the x-axis. This is my x-axis, and it's going to look more or less like so. Okay, we get a reflection about or around the x-axis. And when we create a function h of x, which is going to be equal to f of minus x, the multiplication by minus occurs within the variable only, then the graph of this will be the same as my original function, the same shape, the same size, etc. The same exact form, with the only difference that is going to be reflected about the y-axis. So it's going to look more or less like so. You see, we had it here, and now it's going to appear here. That's what it means to be reflected about the y-axis. So this is what is known as reflections, guys. This is a reflection about the x-axis, and this is a reflection about the y-axis. That's how it works. Very simple stuff. Let's look at another two examples of this. Okay, look at this function. I already have it prepared. Okay, now this one looks more complex, right? This is not what we understand by a parent function. A parent function is kind of like the most simple version of our function. If we know that this is a quadratic function, we know that the simplest version of the quadratic function is simply x squared, okay? Because it's also a parabola, but it's a parabola centered on 0, 0. It's the most simple version of what we understand by the quadratic function, okay? And we usually take this one in order to explain translations, reflections, and so on, but it's not a necessity, okay? I can take any function, no matter what complex, okay? Any function whatsoever. So let's take f of x equals to all of this stuff, and it looks like this. Okay, now I'm gonna produce a function g, and I want the function g to be the reflection about the x-axis of f. So what do I need to do? All I need to do is this: the negative of f of x. And as you can see, this is what we produce: a reflection about the x-axis of my original function. And one more time, I could have written the whole expression minus f of x, but what is f of x? It's all of this. So I could do that: x squared minus 4x plus 5. And as you can see, I get the same graph, okay? This and this is exactly the same thing. If I deactivate this, you can see. If I deactivate this, you can see that they are the same. So we have produced a reflection about the x-axis. Now let's produce a reflection about the y-axis. Let's call the function h. And in order to produce a reflection about the y-axis, what we do is create a function h, which is going to be the same as f of minus x. You see? And we produce this function, or this graph, which is a reflection of this one about the y-axis, right? The y-axis acts as the axis of symmetry of this new figure, which consists of the graphs of two functions. And if I want to write the whole expression, all I need to do is write f, but I'm gonna place the minus inside the variable, so it's gonna look like this: minus, instead of x squared, I'm gonna change x for minus x, like so. That's gonna be my first term, and then we have minus 4 that multiplies minus x, and then plus 5. And as you can see, we get the same reflection about the y-axis. this and this are exactly the same thing. Perfect. One example more in order to finish. What if I give you the good old parabola in its simplest form, also known sometimes as the parent function or the parent graph? Let's reflect it about the x-axis. All I need to do is multiply by minus the whole function, right? If the function is x squared, when I multiply minus x squared, I get a reflection about the x-axis. Simple enough. Now, in here, I'm going to ask you a question. What do you think is going to happen when I try to reflect my original function, which is this? Let me erase this. What do you think is going to happen when I try to reflect it about the y-axis? And I'm going to call that function h. H is going to be the reflection of f about the y-axis. What do you think is going to happen? Anything new or not? It's not going to happen anything, right? Let's see why. In order to produce a reflection about the y-axis, what I need to do is put a minus inside the variable. So it's going to look like this. Minus x to the square. And I get the same thing, right? Which is obvious. If this is my original function and you can imagine reflecting it about the y-axis, you're going to get the same thing. I don't know if you can see it, right? This branch will become now this branch, and this branch will become now this branch, okay? So you're gonna get the same thing, which makes sense, because if you look at the equation of h, the equation that represents h is equal to minus x, all of that to the square, and when you simplify all of this, or when you apply some algebra, you know that this is gonna be equal to minus x times minus x, which is the same as x squared, right? Minus times minus is plus, x times x is x squared. So we can see analytically that h is going to be the same as f. And if they are the same algebraically, they have to be the same geometrically. You see? It makes sense. So not when you try to do reflections, sometimes you're going to get the same thing as before, okay? Okay, guys, so that's how reflections work. Let's stop it right here. And now let's work in the workbook. Thank you.